Κυρίες και κύριοι, καλώς ήρθατε. Έχουμε την τιμή να φιλοξενούμε τον διεθνούς φήμης καθηγητή John Christy. Ο κύριος Christy είναι διακηρυγμένος καθηγητής στο Πανεπιστήμιο της Αλαμπάμα, Huntsville, με τον οποίο είχα την τύχη να συνεργαστώ πάρα πολύ σε πολύ μικρό χρονικό διάστημα, αρκετά χρόνια πριν. Ο κύριος Christy μαζί με τον Roy Spencer έλαβαν το βραβείο της NASA για ανακαλύψεις, προφανώς το οποίο δίνεται σε πολύ λίγους επιστήμονες. Ο κύριος Christy είναι κλιματολόγος και είναι μαζί με τον Roy Spencer οι πρώτοι οι οποίοι μας έδειξαν μέσω πραγματικών παρατηρήσεων από δορυφόρους τη θερμοκρασία στην κατώτερη και ανώτερη τροπόσφαιρα, δηλαδή στο κατώτερο μέρος της ατμόσφαιράς μας. Έχει να μας πει ορισμένα πράγματα τα οποία σίγουρα σας υπόσχομαι δεν πρόκειται να ακούσετε στα βραδινά δελτία ειδήσεων και στα διάφορα παραθυράκια. Είναι μια προσέγγιση η οποία νομίζω θα συζητηθεί. Και πάλι, John.
Okay. Thank you so much, Themas. He has been a wonderful host for us as we've been here in the past few days. I want to also thank the president and the director of the Hellenic Center for Marine Research, I got it right, for having me come here to present some science that we do from Alabama. This will be a little different type of presentation about global warming than I'm sure you have heard before. I'm actually one of the few people in the world who is a true climate scientist. I actually build data sets from scratch, whether they be satellite radiance counts or balloon measurements and so on, to answer questions about the climate. What is the climate doing? Why is it doing it? And so, but I have a personal view on this that I want to weave into what the story is today, and that's where I will start. I had the great fortune of teaching in Africa back in the 1970s. I taught physics and chemistry. There it is. I taught physics and chemistry to the students there, set up a weather station, and just had a wonderful time in Kenya, is where I was, in the rural area of Kenya, not Nairobi. But here's something I learned in Kenya. Every morning, or the energy system of Kenya, if you look at the top picture, you will see a hill with forest on top, and then there's essentially no forest on the bottom. And that's because the energy system in Africa is one that uses wood. And so people constantly get up every morning, the women right here, go to the edge of the forest, chop down wood, put it on their backs, and haul it back by very back-breaking labor. And the sad part about this is seen right here. I think you can see the smoke in this hut, and I've been in many, many African huts having dinner and so on. And it turns out that this is a very toxic kind of a poisonous gas, comes from wood. And so about 2 million children per year die from respiratory diseases of this type of energy system. So I think you see here two drastic environmental problems. The first one up here destroys the wildlife, it destroys the ecology, it destroys the habitat in which many of the wonderful animals from East Africa live. And the second one is here, that now, because of this energy system, many children die every year right now. And this is a system they don't want to maintain. There's got to be a better answer for their energy needs that would also stop this from happening and stop deaths here from happening. So I witnessed this personally as I was a teacher in Africa. Now, so from saying that, I would say, please don't demonize, that's a good Greek word, demonize carbon energy, because without this energy, life is brutal and short. I witnessed it firsthand when I was living in Africa. Without energy, without electrification, without transportation, without industry, life is brutal and short. Now, here are the things we love. Here are the things we are addicted to. We love long life, good health and medical advances, technological process, affordable services, freedom of mobility. You have your automobile, you go where you want, when you want to efficiently utilize your life. Affordable food, abundant, We love natural landscapes. We don't like to see the landscapes that you see now in East Africa that are just denuded. And we love clean air and water. Now, what gets us those? Well, it turns out affordable energy is what is able to make those things happen. If you want to find the worst polluted rivers, you don't go to the rich countries, you go to the poor countries. If you want to find the worst air pollution, you don't go to rich countries, you find that in the poorer countries because of their energy poverty. And so what kind of energy gets us that? Well, nearly all of it is from carbon, burning carbon. Carbon dioxide from coal, natural gas, and oil. About 9% is from nuclear, and about 3% from hydroelectric. We saw a great example of a dam being built up above here. I assume it's going to have a hydroelectric system in it as well. So that's all you see in blue are the great things that energy here provides for us. Okay? Now, there are questions about that kind of energy. Now, carbon dioxide, as I said, is non-toxic. It actually invigorates the biosphere. It makes plants grow. Carbon dioxide is plant food. That's all it is. It increases food production. In fact, about 1/6 of the vegetative food production is due to the increase in carbon dioxide in the last 100 years, as we have put back into the atmosphere the carbon dioxide that had been there millions of years before. But here's the big question. Okay, many, many useful, good, and great things come from carbon energy, but does it have a downside? What might it do to the climate? And that's the big issue that you see displayed about you in the display next door. Well, let me talk a little bit about science here. You will hear statements about consensus of scientists says this or that. But consensus is not science. Consensus is a political notion. And here in the midst of your election process, you know about political things. Very much so. But that is not science. That's people taking votes, people trying to impress, people trying to persuade someone to come to a point of view. But fortunately, 150 years ago, Lord Kelvin told us what science was. He said, all science is numbers. That's what you need to talk about when you talk about climate change or any other kind of science. Let's talk about facts. Let's talk about numbers. So I will show you a number of graphs here that display the information you need to know about climate. My high school physics teacher said this: we should always begin our scientific assessments with the following statement: at our present level of ignorance, we think we know. That's a statement of humility about a complex system like climate. People will tell you they know what the climate is doing and they know why. They're not climate scientists. They're people who have been convinced by a consensus. But people like me who actually look into the insides of the climate system have many more questions than answers. So, what do we know about climate and energy? Well, carbon-based energy produces CO2. CO2 is a greenhouse gas. Greenhouse gases do warm the earth, so there is more CO2 in the atmosphere. That imparts a positive forcing on temperature. So temperature should rise. That should be an indicator of extra CO2. Isn't it that simple? Now, going back to the second one, is that rise in temperature dangerous? How much will it be? Okay. Well, here's an energy diagram. It's pretty complicated. I think all I want you to see is if you look at the greens, coal, blue is natural gas, that's the 87% of energy that eventually ends up to give us transportation, electricity, and industrial production. The solar, wind, and other things are very, very tiny, and that's because they are very expensive to run. And if you look at, remember science, as Lord Kelvin said, is numbers. All science is numbers. Here is where you want to look at a chart like this that shows, well, what's the power density of these type of structures versus things that are viewed to be environmentally sustainable, like solar and wind. And I know there's a lot of solar and wind here. And there are places where that might have some advantage, especially if you're remote places and so on. But you can see that in terms of density, it takes a lot of land to produce a little bit of electricity with solar and wind. In fact, Themis and I were doing some calculations just before this. The new nuclear power plants that might be ready by 2020 will produce about 12,000 watts per meter squared of footprint on the ground. So these are very high density. So in that sense, they use up very little land at all. So you can leave the land for natural systems, unlike what you have in Africa, where the land is being taken for wood. As you can see, wood here is at the bottom. Wood is a terrible source of energy, yet many people in the world depend on it now. And then there's also the cost. The cost of these other energies are very high. That's why they are not growing in terms of demand, and they're not dependable. This little star right here, on these top 4 sources, they are what we call baseload power or on-demand energy. When you turn on the light switch, you want the light to come on. That's the way we use energy. Those top 4 give you energy when you want it, so they are baseload power. The others do not. And that also makes them not economically viable. And I could talk many more minutes about that, but we'll just leave it there. Now, what about carbon dioxide? It is a byproduct of energy production. Carbon dioxide represents progress and development when you think about it. It increases food production, as I said, because carbon dioxide is plant food. And the global atmospheric concentrations are growing at about 0.6% per year. And that leads to about 1 degree C of warming over time for the case in which we have neutral feedbacks. Climate model projections, however, assert 2 to 4 degrees C warming in that time because they have positive feedbacks. So the legislation, the laws that are being considered around the world are based upon this last statement here, that climate models show a positive feedback in the system. Now, I testify before many cases. This is the U.S. Congress right here, but also in federal court and in regulatory boards. And those are very interesting places to testify and show information like this because you are cross-examined. So everyone that goes up on the stage is going to be grilled, is going to be asked questions all the way down the line. So your information better be very good for it to stand in terms of the examination that comes. And so I will show you some of the things that are actually being now that I present in court and in congressional cases. And so, as I said, we build data sets to test hypotheses about global warming. You have a hypothesis, we will build a data set to test it. And what we find here is that climate models tend to overstate or misrepresent the warming. And so how do you test a climate model? How do you define what's called a falsifiable hypothesis to show the model is correct or not? And the way we do it is find a prominent metric that is the main response in the model, the global model. What is the main response in the model when CO2 is added? And then look at that metric. Not the little metric, not what happens in Greece, not what happens in South Africa. What about the global average temperature? That is the simple response metric that you should test. And so let's do one from 1988. NASA scientist James Hansen told us in 1988, this is what's going to happen to the world's temperature. He says, in the orange and the red lines, if we continue on with carbon dioxide emissions as we are, that is what's going to happen to the temperature. If we stop emissions in 2000, that's what the temperature will be. And so that started the entire global warming movement, that global warming is a dangerous thing because the climate models indicate rapid temperature rise. Okay, to a scientist like me, a climate scientist, that's a hypothesis. That's something we can test because we know how to create global temperatures We do it from satellites. We are able to use satellite temperatures around the globe, the whole globe, consistently and uniformly measured to come up with the result, and here's the result. That the real world does not come anywhere close to what those projections are. And I would say as a scientist, and I think some of you who were scientists as well would say, that hypothesis has been falsified. Because this blue warming rate is much, much less than this red and orange warming rate. But that was 24 years ago. What about the absolute latest model results right now that will be used in many reports and assessments about climate change? So these are the latest models, and what they show from 1975 to 2020 are these results here. This is the cooling due to El Chichon volcano. This is the cooling due to the Mount Pinatubo volcano. But otherwise, the carbon dioxide is making the model warm up pretty rapidly. That's a hypothesis. That's something we can test. And here's the test. That the actual global temperatures have seen a little rise, perhaps due to carbon dioxide, but not nearly as much as what the models are projecting. And what we say at this point is that the models show too much sensitivity to carbon dioxide. They hold on to too much heat in these climate models than what the real world does. Those are observations versus models. Now, so let's go to that notion of climate sensitivity and see what we're talking about. The climate models tend to overstate the sensitivity due to missing negative feedbacks. When you have a climate system and you double the carbon dioxide, the impact of doubled carbon dioxide on its own is about 1 degree C, which is not much in terms of the global temperature up and down. What happens in climate models is they come up with these numbers because they add positive feedbacks, that when you warm up the Earth a little, things happen in the models that keep the warming going. The initial and preliminary results my colleague and others have found is that when you use observations, that the result is that there are actually tendency for negative feedbacks to occur. And I'm going to explain it as simply as I can right now. In climate models, when the Earth warms up a little from CO2, the clouds shrink. The cloud coverage shrinks, and the sunlight comes in and heats up the Earth. That's the positive feedback you see. It's not because of the carbon dioxide, that secondary effect. It's because the clouds shrink in the models and the sunlight comes in and heats the Earth. What these observations in the green show is that when you heat up the Earth a little bit, the cloud coverage expands and reflects sunlight and actually cools the Earth. So it's a negative feedback. CO2 warms the Earth a little bit, the cloud response cools the Earth a little bit. And so that's what the observations are suggesting. There have been a number of papers to show this, whereas climate models are all on the very positive side.
Decline and so on.
Okay, we have a question back here.
If the role of the clouds, the positive or negative feedback of the clouds is so crucial for the climate change, why this is not a hot topic in the public literature or even in the research? I've never heard about this role.
Okay, I can say two things. It is a hot topic within the small climate community. It is not a hot topic in the bureaucracy of climate studies because they can understand it. They don't want to say, this is a big thing we don't know the answer to. They want to give answers. You know about bureaucracies, you know about politicians. They want to give the answer. And so you don't want to stand up and say, we don't know how the system works. But like my high school physics teacher said 50 years ago, we should always begin our statements with, at our present level of ignorance, we think we know.
But I'm lost right here. So the increase of CO2 currently has made the cloud coverage bigger or smaller?
Well, the best data set we have is only 10 years old, but it does show an increase in cloud coverage, or actually a lowering of clouds, which makes them better reflectors. So that is in the data. But 10 years, you know, you want to have more time to make a more confident assessment of that. So that's why I kept saying preliminary results show this brightening of the clouds with a warming temperature. So I don't think anyone's saying the world will not warm. CO2 is a greenhouse gas. It has to warm some. But Mother Nature does a lot of other things on this slight forcing.
But people, if I may continue, about this South Pole thing, that the ice shelf is increasing, you say?
The sea ice, yes.
Yeah. Yes, it does. And the North Pole is decreasing. Because we get the feeling that Antarctica is really also melting away. That's what
you're exactly right. I get the same feeling when I read the newspaper.
But do we have a geological explanation of this phenomenon? That one is melting at the north and the other is increasing at the south? And is this repeating itself in the long history of the planet?
You know, there are times when it looks like the poles do opposite things and times when they do the same. It's another one of those questions we can't answer. We just don't know why the system would behave that way. And another part of the answer of that question is, if we could explain it, we could model it in scientifically, but the models don't show an opposite character of each pole.
If a physicist was here, I'm not a physicist, I'm a biologist, but he would probably go out with the idea that we do not have a rigorous science yet about climate change. Is that true?
I have testified in court. I call it climate science is a murky science. Climate science is a murky science. It's like looking through a window that's very murky, it's dirty. We can't see clearly into the science through the window. We're a young science. You know, climate has only been around 20 or 30 years as a science. The system is entirely so complex. How many degrees of freedom in the global atmosphere and ocean? Millions and millions. Do we have the accurate initial conditions to model that? Do we have the accurate equations to determine the evolution of that system? No.
And do you think it will continue that way? Because particle physics...
we have another question back here. Yeah.
Yeah. Actually, it's related. I have two questions. One of them is related to what we just discussed. I want your comments on the melting of the North Pole ice cover. It's presented as something maybe catastrophic, as something really drastic, not to load it too much semantically, but something really drastic. Has this happened in the past any time? And the second question has to do, maybe it's related to this. It is related to this. With the frozen methane and other natural gases found close to the northern pole, either, I don't know exactly where, in the sea maybe, and also in these large quagmires in Siberia, etc. If this is released in the atmosphere, it should have also some significant effect.
Okay, on the first question, the first question about the Arctic sea ice, yes, it has been very thin in the past.
When was that?
In the past 10,000 years, there were many times when it was almost melted through the summer. There are studies that go to the islands up there off of Canada and show where this is the case. In terms of the second question, which was about the methane hydrates, that's a real good question. They tend to be in places deep in the ocean that are cold. And to mix energy down that far takes hundreds, thousands of years. Plus, the atmosphere doesn't have many joules to transmit down. As we were talking about, water has a lot of mass, and therefore it takes a lot of joules of energy just to change the temperature a little bit. So it takes a huge amount of extra energy from the atmosphere to come down and mix to the bottom of the ocean, which is difficult because the ocean is stratified in a way with cold water at the bottom and hot water in the top. And And it's tough for energy to be transmitted down.
These white masks which are frozen in Siberia.
Oh, on land?
These can melt
Yes.
more easily, I guess.
Okay. They are being studied right now, that's all I can say. And the increase in methane has actually slowed in the past 15 years. No one knows why. I would expect it to increase, but for some reason it has almost stopped growing in terms of concentration in the atmosphere.
Goes up, then this methane from Siberia should be released.
And the temperature in Siberia has gone up. And that's why, you know, people are scratching their heads. But remember, methane has a lifespan in the atmosphere that's only about a week or so. It's a reactive gas. So it's not like CO2 that stays for 100, 200 years or so. You know, maybe we're taking methane out faster. I don't know. I really don't know. Yes?
Thank you. I have two questions. The first has to do with opinion. Some people say that the destroy of the tropic forests nowadays is so great, so big, so large, which means that even all the inhabitants of the planet plant a tree every day, it's very difficult to recover this effect and to recover, the earth to recover. And this is my additional to this question is, for areas like Greece, like Mediterranean area, where we have moderate climates, where we have learned, we know that the trees can influence like components in the nature to maintain and to improve locally the moderate climate, holding the soil, making shadow, influencing the wind, and finally influencing to avoid the strong events like storms, which are destroy everything, and erosion and corrosion. This is the one question. And the second is... Okay.
Let me talk about that. I'm not a real expert on the deforestation issue in the tropics. I've seen it. But you make a good point that a tree is like a water pump. It takes water from under the ground and transpires it to the atmosphere, so it's a source of moisture for the air. And remember that picture of Kilimanjaro I showed, Mount Kilimanjaro with the snow going away? There are studies right now showing that because of deforestation around the base of Kilimanjaro, that has removed those pumps that put moisture in the air that create clouds and snow on top. And so in the later years, at least the last 30 or 40 years, that humans might have caused part of that decline, but not because of warming, but because of removing the trees. So you are right that the land surface has an impact on the climate. And remember the other part, when you destroy a forest, you're destroying the habitat of some terrifically important species. And so that's not a good thing to do, I don't think. And so not only do you have a climate effect, you have a biological effect that is very important to try to avoid. These forests do regenerate. It takes a long time for them to come back. And so there will be a time, if they're left alone, that they will eventually return to normal. But it takes a long time in tropical soils, which are poor soils to begin with.
And the second question is, according to your conclusions recently, do you believe that your efforts, the people, scientists who work in all these things, in climate variations or climate changes, some other don't like the variation, do you believe that your efforts are to the correct direction to influence organizations and people who design the actions for the future to have a good path, a good way to stand and to have a good effect in the future for the problems from these climate impacts? Strategic action is good in a good way.
I'll try to answer this question by starting out by saying we should remember that climate scientists are people. And often people believe what they want to believe. And so remember that. Scientists are people, especially climate scientists. What kind of impact? I don't think I'm having much impact on the entire community because it is a community that is totally solidified into an establishment of global warming being a dangerous phenomenon. They truly want that message to be established, and so funding for their programs, publications, they are all wrapped up together to keep that ship moving. There's a lot of inertia there. Where I see a glimmer of hope is in the court system, because in court, the climate scientist is there and he is cross-examined in public, on the record, and he cannot say, yes, my model is accurate. Yes, I have all the parameterizations perfectly done. Yes, I have the initial conditions perfect. And then I present information like I've shown that says, these projections just don't match observations. And that very simple notion carries the day in many places. And so in that arena of regulation, I think I see a glimmer of hope. But my science, the establishment in which I work is very much not easily influenced to these kinds of talks.
So can we hope for better future?
Oh yes, I am an optimist, believe me. I've lived in Africa, I've lived in some pretty tough places, and I see progress all around. What I don't see is dangerous climate change from CO2. I see positive benefits from energy applied to people that are poor and need it. Who's next?
Yes.
Yes.
Yes, I have two questions.
Okay.
One is technical, more or less. We've seen temperatures going down 4,000 years, 5,000 years, 1,000 years. We would like to know how they are measured and how accurate they are. One. And the other question is about the topic of pollution. Climatic change is one, pollution is another. They are interconnected. CO2 also is a pollutant for many people. And how do these things really interconnect? How do pollution affects climatic change?
Okay, that second one's a long answer. I'll try to make it brief. But the first one, usually you want multi-proxy indicators of past climate, not just one thing. Now, I showed you in Greenland what was the borehole temperatures. Those are real temperatures that you measure down a borehole that's filled with some kind of oil that doesn't freeze. And as you go further down in the hole, you go further back in time, because the only forcing on that temperature is what happened at the surface. And so that's a real temperature measurement. Then, to corroborate that, there are many other measurements of plants that were growing, the phenology, warm weather plants that were growing at the time, lack of ice in various places. So that's another indicator that it was very warm back during the mid-Holocene, we call it, about 5, 6, 7, 8,000 years ago. In fact, trees grew all the way to the Arctic perimeter. It was so warm, the forest went all the way there. Today it's just tundra. Now the second question is, you know, carbon dioxide, I don't think it's a pollutant. I think it's plant food. But you are exactly right. Some people think of it as pollution. They call it global warming pollution, I think is what they call it. But when you burn coal, for example, there are a lot of other things that go out. There's sulfur dioxide. That's a toxic gas. In the United States, we spend millions of dollars to scrub it out. There are particulates, ash, that go out. And if they get in your lungs, they're not nice. I mean, this causes tremendous breathing problems, which is why in Africa, all those children are dying because they're breathing those aerosols from the wood fires. Now, the technical part of that is aerosols in the atmosphere do affect the climate. They reflect solar radiation, cooling the Earth, but they absorb infrared radiation, warming the Earth. So which is it? They also affect clouds. They might create more brighter clouds or fewer clouds. It's hard to know. So the aerosols have a really complicated part. And there are people in my group at the University of Alabama in Huntsville that are working very hard on trying to understand what is the climate impact of all of these aerosols. We know they're not very good for health. So removing them from the air would be a good thing. And we are doing that in many countries. Now, one solution, burn natural gas. That doesn't have the aerosols.
So what is the reason for this misunderstanding or misleading by governments or the ecologists or media? Who makes money from this? And second question.
You must be a journalist. What is the importance of it? Yes.
What about the other effects? You already said some of them. If your grandchildren come to you and say, grandfather, where is the best climate for us to live our lives? Would you send them next to a huge industry that produces carbon dioxide?
Well, let me answer the next one, the last one first. My grandchildren, as they grow up, will be living in a better world, because I'm an optimist. And these situations, we have seen great improvement over the past 20 years. The United States, particulate matter, aerosol pollution has dropped dramatically because of these regulations to get poisonous things out of the air. But CO2, no, that's not a problem for them. The first question goes to the motivation, and I would just say there are many things that motivate people and industries. Some industries are very keen to make money off of green energy. Green energy requires government money because it can't make it in the marketplace. And so you will want to have laws passed that benefit, that take the taxpayers' money and gives it to you. In fact, I was at one big industry, if I would name it, you would all know it, a huge company. Their business plan was get the government to force the public to buy our product. Now that's not democracy or freedom in my view, but they will manage the system to get regulations passed that make their product more affordable and make the other products more costly. So there are industries that play that game. And I don't know if they are, I think they might just be driven by profit. Whether the earth is saved or not, it might be a different question, but that's one. So that's one motivation. Other motivations are just people. Some people like attention, and the media have been very good to give people with terrible stories a great forum in which to speak. I mean, if I came to the media and said, the global average temperature is just normal today. Well, who wants that story? You know, I've got to have a real big story about people dying or something. That's about the best I can do for an answer on that.
Okay, yeah.
Thank you. Thank you all.